Today we are going to be in section 1.4 and we are talking about one-sided limits. One-sided limits. And this thing known as continuity. So we know how to find limits, and we have this thing called continuity. Continuity in general is a continuous function, is a function continuous. And we're going to talk about that first. So for our continuity, we have an informal definition and we have a formal. You are expected to know the formal definition. The informal one is just kind of an easier way to think of what continuity is. So we're going to start there first. We're going to say informal. And our informal definition is a continuous function is a function with no holes, gaps, or jumps when you're looking at your graph. No holes, gaps, or jumps. The formal definition of this is first, your function needs to be defined at a point. F of C needs to be defined. The second part would be, I don't know what in the world that is. The second part is that the limit of f of x as x goes to c has to exist. So the limit at that same point has to exist. And then lastly, the limit of f of x as x goes to that point has to actually be equal to f of c. And this is the formal definition of saying a function with no holes, gaps, or jumps. Next, we are going to talk about our one-sided limits. So we're going to kind of hit the definitions of both right away. So our one-sided limits. And with our one-sided limits, we're just going to define a couple things first. From the right side, if we're looking at a limit, so it's one-sided, which means there's got to be a right and a left. If we're looking at a right-sided limit, the notation is going to look super similar as it would to a left. With it, we would say the limit of f of x as x goes to c has to be equal to L. But because it's coming from the right side, if you think about it and you're tracing a graph from the right side, it's coming from that positive side, so it's going to be labeled as x goes to c with a plus sign at the top. That plus sign means it's coming from the positive side of your graph, which if we were to draw a graph to kind of help explain this just a little bit, and let's use something similar to a graph that you did in your homework last week. And it's going to look I don't want a straight line. It's going to be a parabola, and that one end is going to be an open circle. And the second part, so it looks something like this. And we'll just pretend this is at like 1. Okay, we would say our right-sided limit as x goes to 1 would be 0. Or in this case, we're just going to call it L. Your left-sided limit, we're going to write it as the limit of f of x, not over, as x goes to c is going to also be equal to L. Okay, and with this L is just some arbitrary number, but since it's coming from the left side, that's coming from the negative side of the x-axis. And with it, if we were to look at just this function or this graph in general, we would say, hey, that limit as x goes to 1 doesn't exist because they go to 2 different points. But if we look at it coming from the right side, we would say, hey, it goes to 0. The left side, you say, it goes to 1. So We're not asking for the limit of the whole thing. We're just asking for the limit of your function. Okay, and with this, let's look at an example super quick. With our first example today, and you're going to need to graph this. So get your graphing calculators out. We're going to have the limit of the square root of 4 minus x squared. And we're looking at it x as it goes to 2, or sorry, as it goes to negative 2 from the right side. And then we also want to look at the limit of 4 minus x squared as x goes to negative 2 from the left side. And with this, hopefully we can see some things happening. So go ahead and graph this real quick. And in your graph, you should notice a couple things. You should first, actually that line is not even straight. Just looking at the function, you should notice that our two critical values are going to be at negative 2 and 2. And you should get a graph that looks something similar to this. This point's at negative 2, this point is at 2. So if we look at our graph going to negative 2 from the right side, we're just going to kind of follow this along. Negative 2 from the right side, it's going, boom. And it stops at 0. So from the right side, we know our limit is 0. Now when we go from the left side, notice there is nothing in our graph that is to the left of 2, or sorry, negative 2. And since there's nothing for us to trace, we just say that this does not exist. So since we can't trace anything from the left side of negative 2 because there's no function to trace, then we would say that it does not exist, and that would actually be completed. And with this, we are going to use this knowledge of our right and left, our one-sided limits, to tell us, or to write our definition of the existence of a limit. Definition of the existence of a limit. And what that definition is going to state is fairly simple. If the limit of f of x as x goes to some c from the right side equals L, and the limit of f of x as x goes to c from the left side is also equal to L. So it states the limit of f of x as x goes to c from the right equals L, and the limit of f of x as x goes to c from the left side equals L. We're going to say if and only if, since this is a definition, it has to be an if and only if statement. We can then state that the limit as x goes to c in general of f of x equals L. Basically stating exactly what we worked on last week. If your limit is going to exist at a point, it has to be approaching the same thing from the left and the right. And this is the mathematical way to state that. Okay, so if your limit is going to exist, it has to approach the same value from the left and the right, and this is just the mathematical definition to say that. Thinking back to geometry, which was a while ago, in general in geometry, we said we write our definitions as biconditional statements or if and only if statements, and that's exactly what we just did. Next, we're going to look at the definition of continuity on a closed interval. So the definition of continuity on a closed interval. Definition of continuity on a closed interval, and with it, it's going to be fairly simple. And I'm going to actually start writing with this because it's a little bit cleaner. It's going to state that f is continuous on, and we're going to say a closed interval, so bracket a to b. So we're defining f to be on a closed bracket a to b if it is continuous on the open interval a to b and the limit, so the limit as x goes to a from the right side of f of x equals f of a, and the limit as x goes to b from the left side of f of x equals f of b. So let's read that again. It says f is continuous on a to closed interval a to b if it is continuous on every point between your endpoints and the limit at each endpoint exists. And that is what it's trying to tell us. And with that, we're going to actually use this in an example just to kind of explain what we're talking about. So to begin, the example we're going to look at to explain this is we're looking at the function f of x equals the square root of 5 minus x squared. And with it, we need to figure out what is our domain going to be. Is it going to, well, in general, we'll just start there. What is our domain of our radical function? And in order to figure it out, we know under a square root, everything has to be positive. So we need to figure out when does 5 minus x squared equal 0. Because that is 0 is your changing point from positive to negative. So first we need to solve for x. So we know 5 is equal to x squared. Or we can just say that x is equal to the positive and negative of root 5. And if we were to test this, a point, let's say we substitute in 0 into our function, we know that it's going to be between negative root 5 and positive root 5, so we would state that your domain is negative root 5 to positive root 5. And we are including those endpoints, and this is actually our A and our B that we just talked about in our definition. So since we know that it is continuous from A to B, and we know that because if you throw in the number 0, which is between those 2 points, it comes back with a real number. Then we just need to test that your limit of f of x as x goes to negative root 5 from the right side. If you were to substitute that in, that gives you 0, which if we also substitute that into our function, we get our f of negative root 5. 0 is equal to both of those, so it's true for our left endpoint. And if we check our limit of f of x as x goes to positive root 5 from the left side, well, that's going to be equal to 0, which is also equal to f of root 5. And since we just proved our point, we're continuous from A to B, and we just proved that our limit and our function are equivalent, we have now proved that we have continuity on our interval. And that would actually finish this problem. With this, there are some properties of continuity that you can look up on your own in your textbook. The properties, and this just looks at various functions, our properties of continuity are on page 75, and it talks about our different types of functions. And we know pretty much all of our functions are always going to be continuous on their domain. With it, you can look more into that as you would like, but yeah, page 75 has all of our rules and our definitions for that. Okay, and then the last thing we're going to look at today is this thing known as the intermediate value theorem, and I'm going to